Radio Systems Design, Module 5, Modulation Bandwidth. Today we'll be talking about the bandwidth of digital modulated signals, about the concept of intersymbol interference. Then we'll talk about pulse shaping, in particular Nyquist and raised cosine filters, and finally a little bit about bandwidth efficiency. So we need to think about what the bandwidth of a pulse stream is. When we were describing analog modulation, we sort of naturally talked about it as a spectrum or a series of frequencies that created our signal. But when we talk about digital modulation, we're thinking more about just a stream of ones and zeros or pulses. And we know that a square pulse in the time domain extends as a sinc function in the frequency domain, and that the bandwidth in the frequency domain, if you will, is tied to the period here, TB, ties directly right here to the bandwidth. But you notice this really isn't our bandwidth because we've got all of this other stuff here. And this is because the sharp transitions that occur in, if you think about an ideal bit stream, actually turn into an infinite bandwidth, which is a real problem because the spectrum as it is now is very crowded. And if you think about the olden days with FM radio, you know, the reason you couldn't put more stations on the dial was because you needed a certain amount of space between them because their bandwidth was a certain size. If each one of those started transmitting a digital signal, they would overlap over all of them nearby. So for digital modulation, we've got to figure out some way to fix this modulation bandwidth creep. So let's take a look at the bandwidth of a binary phase shift key. So we've got our digital pulse stream down here on the left, and we've got our cosine, and if we're multiplying in the time domain, we just do a convolution in the frequency domain. And we end up with the spectrum shown here, and as I said, we can't transmit all of this extra amount that we'd like to. And so you might think, as I would have thought initially, that this is no problem. Let's just come in here and let's just do a filter, right? That just gives us the center lobe and we'll just get rid of this back lobe. And if we looked at that in the frequency domain, that would solve our spectrum problem. But the question is, if we just put a filter like that in, what would it do to our time domain signal? This is where the idea of intersymbol interference comes in. So we need to limit the bandwidth of the baseband signal. And what happens if we just do the filtering I mentioned? We just go in and we get rid of this. Well, what we do is we end up just smoothing out each pulse. And that in itself isn't a problem, but the pulse gets smoothed out and it kind of spills over onto the next pulse. And so what you have is at this point in time, you've got not only the response from the pulse you care about, but you've got all of this energy from previous pulses kind of spilling in here and causing interference. Because remember, each unit of time, we're transmitting a symbol. And remember, that symbol can be a single bit, it could be 2 bits, it could be 3 bits, whatever it is our modulation scheme is. We continue to transmit at the same rate. We get higher data by having higher complexity modulation. So in this time t, we get this spillover, and we don't know if the signal we're receiving is due to the current signal or due to what came before this. And as each pulse spills in, it's what we call intersymbol interference. And it results in distortion and ultimately in error in the detection of the signal. So let's have a thought here. Instead of blindly filtering the signal, maybe we can shape the pulses to occupy less bandwidth. What if we found a way to make a smoother transition between each pulse? So here on the left you can see a smoother transition, and the resulting filter might look like what we see over here, and we could still maybe filter out this extra piece over here on the right that maybe wouldn't affect it too much in the time domain. So the idea is there's some way that we can filter our time domain signal to give us a little bit more of a very limited frequency signal. So it turns out there is a solution, and it's called a Nyquist pulse. So Nyquist noticed that these pulses, when we smooth them, basically when we try to filter them in the frequency domain. So if we go to frequency, if we try to build this low-pass filter we talked about, the pulses end up going from a square pulse to this pulse where the sides have some signal that will interfere with future pulses. And the insight he had was, well, maybe this isn't so bad if this is exactly zero when our next pulse is. And so what he did is he proposed a smart pulse shape. And what he basically said was, first of all, notice this plot is in the time domain. If you remember, the Fourier transform or inverse Fourier transform of a box in the spectral domain would give you a sinc in the time domain as the impulse function, right? The impulse response of the filter. And the reason why he thought this would be a good idea is if you could do a filter that would create a pulse that at our time 0 we saw the pulse we wanted, and at the next sampling point it was 0, then it would have no effect on our next pulse. And so no intersymbol interference would be introduced. And so this is an important one to take a look at, is if I sample the dark black curve here, and I come along and the dark black curve is 0 here, that means that I could sample here and get the gray curve and there would be no effect of the black curve. Just as I could sample here and get the dashed curve and there'd be no effect of either the gray or the black curve. So the key isn't that we're getting rid of these tails. We're just making sure that at the point we want to sample, at the point we care about, that all of the tails are 0. And so this is kind of a clever trick he figured out. And Nyquist realized that not only does it remove the intersymbol interference, but it also results in the absolute minimum bandwidth for the modulated signal, which would be ideal, because basically this is saying this is the smallest bandwidth you can get to transmit the pulse information that you'd like to. So with a Nyquist pulse, the modulated RF signal occupies 1 over TB. So the total bandwidth here is 1 over TB, right, for frequency that's there. And so this would be the minimum bandwidth that you could use. It turns out, though, it's actually not very easy to create a Nyquist pulse. And so people have looked at close approximations, and one of the best one is a raised cosine filter or raised cosine pulse. And this is the time domain formula for the pulse shape. And on the right is actually the bandwidth. And the reason this is called a raised cosine is it's actually defined as 0, and then we do a cosine up to here, and then we keep this flat right there. And these are done digitally, so there's some digital signal processing that figures out how to shape this in the frequency domain. And the bandwidth is really, because this is sort of an artificially designed filter, is the distance between these two edges, because it really is 0 out here and 0 out here theoretically. So the bandwidth is simply 1 plus alpha over TB. And if you're wondering what is this alpha, well, this alpha shows up right here, and depending upon the alpha, this will smooth out, or it can actually become even sharper, with it always having the same inflection point, and it'll result in slightly different tails going on to here. And typically alpha is chosen to be between 0.3 and 0.5, and it has to do with the ability to achieve the filter, because as you can imagine, the sharper you get this, the harder it's going to be to actually implement. So our total bandwidth of the filter is 1 plus alpha over TB. I'll just let you know right now, this is an equation you need to know. If I give you alpha, you need to know TB. It's not so hard though, because basically the bandwidth is roughly 30 to 40% larger than 1 over the period of our symbol rate. So I'd like to show you the effects of pulse filtering. And to start with, let's take a look at a random sequence of rectangular pulses. So I'm just going to hit play here, and you can see I'm just generating a random sequence of ones and zeros. And the rectangular because of pretty much just a sharp edge. So this is sort of the digital data that we think of. And the question now that we want to answer is, what does this look like when we filter this? Because as we know that the spectrum of these sharp edges is going to create a very wide spectrum, and we don't want to transmit that. We want to somehow limit that. So let's actually go and take a look at the spectrum of the rectangular pulse. So I show it here in brown, and you can see the spectrum is actually quite wide. So it's continuing out here, and would continue on forever if we had infinitely sharp edges. And so we want to attach some filters in order to limit the bandwidth. And I'm going to look at 3 different types of filters. One is a low-pass filter, and that's shown here sort of in the pink. And you can see it's a standard flat, and then it tapers off here so that it filters out just the lower frequencies. And this may be just a simple multipole low-pass filter. We then have what we studied in lecture, a root cosine filter, and that is this red filter here. And you notice that it has a very tight bandwidth. And the reason it does is because the cosine has an impulse response that looks like a sinc function. We know a sinc function in the time domain would give us a perfect rectangle in the frequency domain. So the root cosine impulse response was basically generated to give us the sharpest sharpest filter we could get in the frequency domain. And then I also have here something called an RRC. This is a root raised cosine, and this is sometimes used by in systems where you create your root cosine by cascading 2 root raised cosine. So this is just the square root in the frequency domain of the root cosine, so that when you cascade them, you end up basically creating a root cosine. And the reason why you cascade is you might put 1 root raised cosine on the transmitter and 1 on the receiver end. So our goal is to try to use these 3 different filters to limit the bandwidth of what we're going to transmit. So let's go take a look at what the pulses look like from each one of these different types of filters. And I'm just going to rerun this simulation so you can see it. The pulse waveform is in the back, and the 3 different filtered waveforms are here. The blue is the low pass, pink is the raised cosine, and red is the root raised cosine. Just for exactness, I'll mention here that I have delayed each one of these streams so that they overlap on the center of the digital stream, so you can compare them. The delay of each filter is different, so if you just hook this input into the 3 filters, you get different delays of pulse sequences. So I've aligned them so that we can compare them together. So let's just take a look. And so here's our random stream, and you can see we get random pulses from each one of these. And it's pretty clear from the root cosine and the raised cosine and the root raised cosine that we get these sort of sinc function pulses. Here's a great example on the left. Both of these look like a nice sinc pulse. And you see that the low pass filter, it's not too bad. We get a little bit of a pulse, but you can see that it's slightly delayed. And it also changes depending on what came before. They all change on what comes before, but the low pass seems to be a little bit less ideal, a little bit less like a series of sinc pulses. However, to be honest with you, I really couldn't say that the pink or the red or the blue, that one's better than the other. I can sort of see that pink and red look a little bit better based upon our target sinc function, but you know, the blue seems to have peaks in the same areas. So what we want to do is figure out a way where we can better compare these two, and the way to do that is basically to think about a receiver. How would we receive these pulses, and what would they look like? And so if you imagine that you're a receiver, what you're going to do is see these waveforms coming in, and you're going to be sampling. And what you'd like to do is sample at the right point so that when it's high, you get a high value or a 1, and when it's low, you get a low value or a 0. And so what I've done is I've plotted the same thing we had before with a sequence of sample pulses, and you can see that these sampling are happening at the peaks. So the basic idea is I would say, okay, this is a 1, this is a 0, a 0, a 0, this is a 1, this is a 1. It doesn't have to be at the top, but you can see it's pretty high there, it's pretty high there, so that'd be a 1 and a 1, and we get a 0, and so forth. So you could do this by hand and try to compare, but a nicer way to do this, and the way that industry does this, is to look at what's called an eye diagram. And this is basically an eye diagram that helps you take a long series of data and see how well it is lining up with a synchronized pulse stream and how well you might receive that data. So what I'd like to do now is actually look at a cartoon example of a eye diagram. But before I show you the eye diagram, I'm going to show you how it's constructed. So now I'd like to explain how an eye diagram is created. And what I did is I took the raised cosine waveform, so that's this waveform in brown here, and I imported it into MATLAB. And so here is basically 100 microseconds of that signal. And what I'm going to do is plot 3 symbols, which happens to be 3 microseconds in this simulation. What I'm going to do is plot 3 symbols at a time down below, but I'm going to march along the top and just keep overlapping those symbols, or sorry, those waveforms on top of here. And once I start clicking, it'll be pretty obvious what's going on. So I take the first waveform, then I just overlay the second one, which is basically the next 3 symbols, next 3 microseconds. Then I do the next one, I do the next one. And so far it doesn't look very good, but let's just keep on moving at this, and I keep on going, overlapping, 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 overlapping. And you can see it doesn't matter if my input's random because I'm just overlapping, and I might do this over thousands and thousands of samples. And you should be able to see right away that there are certain points in time where all the waveforms clearly can make a 1 or can make a 0. And this says that if we were to come in and sample right at this time, we'd get exactly our 1s and 0s as we planned. And this is what's beautiful about the raised cosine, is if we use this filter, even though we get sort of this wobbly signal, if we overlap them, we can see that there is a time and phase delay that we can sample them out and get exactly 1s and 0s. And you can see that the transitions between them is the transitions that we see here, and that varies between pulse sequences, but retrieving a 1 and 0 can actually be very clean. So this is how we create an eye diagram, by overlapping these. And so let's go back to our simulation. What I'd like to do now is take a look at the exact eye diagrams from our simulation example. I'll go ahead and run this. And you can see the transitions are changing around, but these points on the raised cosine are staying exactly in the same point. And so in the bottom we have the rectangular pulse, and this is pretty easy. If I come and sample right here, or I come and sample right here, I'm always going to get my 1s or 0s. But let's go look at the effect of each one of the filters. This is where we really see why the raised cosine is so much better than other filters. So if you look, if we sample right here, we would get exactly our 1 and 0. Same here and same here. So this gives us an exact point. This area here is called an eye. That's why it's called an eye diagram. And you can see as we change filters that eye can get smaller. And so people like to talk about the closing of the eye, or how big the eye is basically determination of how clear we can find a 1 and a 0 at a single point. So let's look at the low pass filter. Even though it was kind of hard to tell from the time domain waveforms, it's clear here there's a fuzzy point where we would be sampling. So the waveforms aren't always at the same point. And also the crossovers. If you notice here, it's clear to see where the crossover is here. The crossover here is a bit unclear. Not that we care about it, but it's showing you sort of the variability. Now the raised root cosine, I included this because if you look, just a simple difference between a raised root cosine and a root raised cosine and a raised cosine is seen right here. The root raised cosine has quite a bit of variation around the single point where we would sample, whereas the root cosine doesn't. So when you look at the eye diagram, it's very easy to see that the raised cosine, the one at the top here, provides a almost ideal point for sampling. All right, talking a little bit about bits versus symbols, we learned that a stream of pulses occupies a bandwidth of RP to 2RP, where RP denotes the pulse rate and the bandwidth of, actually I'll say that the RP relates to 1 over TP. And if you're wondering why is it in between, well, if you look at this, if alpha 0, this is simply, right, this is simply 1 over TP. And if alpha is 1, then this would be 2 over TP, right? So that's what we're looking possibly between, is 1 and 2 over TP. And it depends upon the pulse shape. In binary modulation, each pulse represents a bit. However, as we talked before, pulses can also represent a symbol. And this is important because each pulse has a fixed bandwidth. And we go back to this idea that I have my symbol, right? It has a fixed bandwidth, but the number of bits that the symbol can transmit depends upon my modulation. Okay, so the idea is we have a fixed bandwidth which depends upon our repetition rate. It also depends upon alpha, and that is the symbol. So each pulse we're sending represents a symbol, but depending upon the modulation architecture, it could have any number of bits that are associated with that. So I want to talk a little bit about bandwidth efficiency, because this is what it all comes down to and why we care about this. If we assume we're sending RP Nyquist pulses per second, the signal occupies a bandwidth of RP hertz, as we just discussed. And so that's one pulse being transmitted RP times per second, and so we have RP hertz as our bandwidth. But each pulse represents one symbol. So basically, the pulse is what we're sending physically, but in reality, in our modulation scheme, it's actually a symbol. And so in binary modulation, each symbol represents 1 bit, so we're transmitting 1 bit per second per hertz. But if we can improve the spectral efficiency by transmitting more bits per symbol, because each symbol has a fixed bandwidth, if we can increase the modulation complexity, then we can increase the number of bits transmitted. And in an M-ary modulation, each symbol, or you could say pulse, right, represents k bits. So you end up with a spectral efficiency of k bits per second per hertz. And once again, this goes back to the same idea that our bandwidth is determined by our pulse, not by the number of bits. The way we get more bits per pulse is we just basically have more states, if you will. And I'll just draw you a real quick cartoon. You can think about it, if I had a pulse that was this high, and a pulse that was this high, and a pulse that was this high, each one has the same bandwidth, but they represent 3 different heights, and so 3 different pieces of information. And so that's how we can get to a much higher spectral efficiency, meaning how many bits are you transmitting for a given bandwidth. And so this final slide does a comparison of different modulation architectures, and there's actually a really nice reference down here in the bottom that actually summarizes this in the previous module. On the left here is bit error rate. This is basically a bit error rate of 10 to the minus 6 says that we can transmit 10 to the 6 bits and get one of them wrong. And then this is the carrier to noise ratio, and this is basically like signal to noise. It's basically letting us know how much power we need in our carrier in reference to noise in order to get a certain bit error rate. And so let's just take this 10 to the 6, and what we notice is that BPSK needs a lower carrier power for a given noise, and this is because the symbols are spaced farther apart, as we described before. And as we get to higher and higher modulation schemes, these modulation schemes will have a requirement for more and more carrier power, and the reason is that the constellations are getting closer together. And I think a really interesting one to look at right here is this 8 PSK and 8 QAM, because if you remember, we talked about before, if we have a PSK, let's see if I'll get this right. If here's our 8 PSK and we've got a 8 QAM, so maybe it goes like this, that we can actually have a the same intersymbol distance for lower overall power than we did over here. And so that's why we can see that QAM can have a slightly lower carrier power and get the same spectral efficiency. And I'll just point out here, just to go over again, BPSK, K is equal to 1, and so we get a spectral efficiency of 1. QPSK, we have 2 bits, and so the spectral efficiency is 2. And generally, I'll write that as A to the spectral efficiency. And for 8 PSK, we've got eta equals 3. And you can pretty much tell 2 to the K, right, equals the total number of symbols, right? So 8 is 2 to the 3, 16 is going to be 2 to the 4, so the spectral efficiency of 16 QAM is going to be equal to 4, and then finally 64 is going to be a spectral efficiency of 6. So you can see as we march up, our spectral efficiency increases by K, 1, 2, 3, 4, and 6. But if you noticed, we go from 2 to 4, and then 4 to 6. 2 had 4 symbols, so an eta equals 2 had 4 symbols, and eta equals 4 had 16 symbols, so the difference is 12. But if I go to eta equals 16, I now have, let me see if I can get the math right, this is 64, and the difference is 48. The reason I'm showing you this is, as you go up in modulation scheme, it's not a linear. Meaning we can go to a higher modulation scheme to get a higher spectral efficiency, a higher K bits per second per hertz. However, it gets harder and harder and harder and harder. And so typically, most radios are operating somewhere between QPSK, and there actually is a 1024 QAM that's used, but that's pretty much the limit of where people go. And when they're operating on 1024 QAM, these are usually very low frequency or low symbol rates. And finally, I wanted to talk a little bit about constellation diagrams. We talked before about this being the I and Q, and this is with a rectangular pulse. But now that we've introduced all of these very nice filtered pulses, and from the video that you saw the pulses look more like this. Our constellation, if we were to measure it, looks very messy, and it's because all of these transitions between each constellation get overlaid. You can still see that we're meeting the points that we expect to meet for 16 QAM. But the constellation, when actually measured in the lab, gets much more cloudy. And so one of the ways we can do that is we can actually add persistence, and what that does is it tends to darken in the spots where we see a lot of pulses, and it makes these areas less bright. But basically just a visual way of doing this. As we mentioned before, a better way to see exactly the quality of your constellation, whether you're really getting good rejection of intersymbol interference, is to go and try and look at an eye diagram. So to summarize, we looked at bandwidth and digital modulation, intersymbol interference. We talked about pulse shaping, namely Nyquist and raised cosine, pulses and filters, and we also finally discussed bandwidth efficiency.